Okay, so hi everyone. My name is Lauren Doyle and I'm a postdoc at the University of Warwick. And today I'm going to be talking to you a bit about some of the work I've been doing on two systems, WAS 166 and WAS 131 with ESPRESSO data. So we know that stars rotate, and you can see this here by the blue regions moving towards you and the red regions moving away from you. So if we introduce a transiting planet to this, some of the red and blue starlight is blocked, and this causes an imbalance in the velocities, also known as the Roster-McLaughlin effect. Using spectroscopic observations, we can use this imbalance in velocity to determine the alignment of the planet to the stellar spin axis. And this is also known as the projected obliquity. And this is quite important when you're considering the formation and evolution of planetary systems. So in this talk, I'm going to be using the reloaded Roster-McLaughlin technique to explore the impact of granulation on the projected obliquity. So to do this, we isolate the starlight behind the planet by subtracting in-transit observations from out-of-transit observations. And in this video on the right, I'm showing that where the isolated starlight, we're operating on the cross correlation function, or the CCF, which is basically just like a composite of all the absorption spectral lines, sorry. And then we're scaling the CCFs using transit light curves to allow for this direct subtraction. So this video was kindly given to me by Sam, and you can see in the top plot, you've got the planet crossing the stellar disk. And then in the middle panel, you've got the local CCF. So these are the in-transit subtracted from the out-of-transit. And then in the bottom panel, you've just got a top-down view of this. And you can see there's a shift in the centroid as the planet tracks across the stellar disk. But on the surface of sun-like stars, we also have hot bubbles of plasma that are continuously rising to the surface before they cool and fall back into intergranular lanes. And here I'm showing a simulation of what these granules look like at disk center and near the limb of the star, which I think got messed up when I transferred my presentation, but it's okay. So the one in the square one is at the limb, is at the center, and then the other one that's above it is now at the limb. So you can see that the line of sight changes. The line of sight causes the net convective velocity of these granules to change. Because at the limb, you're looking more into the walls, whereas at the center of the star, you're looking more at the tops of the granules. And you can see this here in the plot for simulations of the sun, where at this center, you've got a limb angle of 0. There's a small contribution, but then out to the limbs at about 80 degrees, the velocity contribution is higher, around 250 to 300 meters per second. So on top of the stellar rotation, we've also got the convective velocities, and that makes up the total velocities that we have of the star, and that's what I'm showing here. But we don't, this changes as a function of spectral type and magnetic field, and you can see this in the plot here for simulations. There is no known formula to fit for the center to limb to fit for the velocities as a function of limb angle. So what we're doing is we're going to fit different polynomial models to try and capture the trend. Okay, so let's go on to some data. So I'm going to talk about WAS 166 first. It's a transiting super Neptune within the Neptune desert. The host star is bright, V equals 9.4. It's an F9 main sequence star with an effective temperature of 6,050 Kelvin. We have two transits of WAS 16B from ESPRESSO on the 31st of December 2020 and the 18th of February 2021. And here I'm showing the isolated starlight behind the planet, also known as the local CCFs of WAS 166 in the top panel. So it's basically what we showed in the video before, but now this is real data. The bottom panel then again is the top map view of the CCFs, and you can see the shift in velocity in the CCF centroid. Just to note here that the light gray lines are out of transit, and then the dark gray lines are the unbinned in transit. For this particular data, the colored lines represent bin to 10 minutes, and that's because we want to increase the signal to noise and also bin out any potential P modes in the data. So that will be continued for this target. So once we have the local CCS, we then want to fit a Gaussian to them to extract the centroid, which represents the velocity at the stellar surface behind the planet. So here I've done this for WAS 166, where the gray points are the observations again, which are unbinned, and then color points are binned on 10 minutes. And they're color coded according to their limb angle, so from the center of the star out to the limb. We fit these local RVs using a model, and this model consists of a key formula which depends on the position of the transiting planet center with respect to the stellar disk, the sky projected obliquity, the stellar inclination, equatorial rotational velocity, quadratic stellar limb darkening, and center to limb convective variations of the star. And the colored lines in this top plot represent those different models where we assume different conditions. So the first one, the red one, is solid body rotation on its own. Blue is then solid body plus a center to limb linear contribution. Green is solid body plus a quadratic center to limb contribution. And orange is solid body plus a cubic center to limb contribution. And overall, we find the best fit to the data is the solid body plus the cubic center to limb contribution, where the projected obliquity and the V sin I measurements are shown here on the board as well. So we're also interested in this net convective blue shift as it varies across the stellar disk. And the net convective velocity shift caused by granules changes as a function of limb angle, so from the center out to the limb of the star due to line of sight changes, which I explained earlier. So in this plot, I'm showing the solid body model alone, subtracted from the local RVs, and from the previous plot. And I'm now just plotting them as a function of limb angle instead of phase. So 1 is the center of the star and then out to the limb at like 0.2. As you can see, there's about a 2 kilometers per second variation, which changes from the disk center out to the limb, about mu equals to 0.2. And this could result from center to limb variations. Now, you might be asking yourself, why do we care about such a small change? But the reason is it can have impacts on your measurements of your projected obliquity. And if this is out, then you could skew your understanding of the formation and evolution of the planetary system. So in simulation work, it has been found that if you don't correct for center to limb or account for center to limb variations, your obliquity can be out by about 10 to 20 degrees. For WASP 166, what we found was that the obliquity was out by about 9 degrees when we accounted for the center to limb variations by the cubic polynomial fit. For WASP 166 as well, these center to limb variations are on the order of 1 to 2 kilometers per second. If we're expecting a differential rotational shear on this star of about 0.5, the change in velocity would be about 2.5 kilometers per second from pole to pole. So therefore, this change could be hidden by the center to limb variations. And here what we did was we used the center to limb variations to then fit a differential rotation model, and we were able to pick out a tentative detection where there was a bit of a degeneracy between where the star is pointing towards or away from us. And here, this plot I'm showing is the optimal parameter space for detecting differential rotation over solid body. And you can see that these two scenarios do fit in the dark green regions, which suggests that we should be able to get a differential rotation detection. If you're interested in this work, the ESPRESSO data has also been used by my colleague Marina. She has a poster here, number 75, where she looks at detecting a potential blue shift of water signal and presence of clouds in the atmosphere of WASP 166. So please do go and check that out. So I'm just going to move on a little bit to talk about WASP 131. It's a system of a bloated Saturn mass planet on a G0 type star with effective temperature 6030. For this target, we had a number of ground-based transit light curves, and you can see that here, where we fit for the planetary properties to determine the most updated ephemeris. This target has been looked at in previous studies by Vidad Novak using HARPS transit observations to determine the projected obliquity in V sin I, which I'm showing here. And again, I've plotted this on the optimal parameter space for detecting DR, where we should be able to pick out a differential rotational signal from the star. I have 2 ESPRESSO transits on this target on the 8th and 24th of March 2021, and I'm now going to talk about the reloaded technique on that. So here again are the local RVs, the occulted starlight for WASP 131. We fit a solid body model in blue, solid body plus linear center to limb model in red, and a differential rotation model in yellow. And overall, we found that the differential rotational model was the best fit to the data. And you can see the properties of the fit here, where we find that the star is inclined towards us at 41 degrees. It's highly misaligned with the projected obliquity of 162 degrees. And you can see in the schematic on the top. We also determined a differential rotational shear of 0.61, where the poles of the star rotate 60% slower than the equator. And since we're able to determine the stellar inclination, we also derived the true 3D obliquity psi of 123 degrees. So this means that WASP 131 is on a nearly retrograde orbit, and it joins a group of misaligned planets with a preference for a polar orbit. So even though the differential rotation alone, not considering any center to limb, was the best fit, a solid body plus linear center to limb was the best fit among just the solid body models for this target. So you can see this in the figure to the left here, where we detected CLV. And in the DR model, we wanted to make sure that we weren't confusing center to limb variations and differential rotation. So this is what I'm showing here, where we're plotting, comparing the linear center to limb variation from the solid body fit and the differential shear contribution of the local RVs. And overall, we find the shape of the solid body residuals is similar to both the linear center to limb contribution and differential shear contribution. However, there are a few points at ingress and egress, along with some in the middle about phase 0 that are favorable towards the differential rotation model. So this explains why the differential rotation model is favored amongst all models. And if we had a bit more precision in our data and we're able to sample the limbs a bit better, then maybe we would be able to detect the center to limb and as well as the differential rotation. So I'm kind of running out of time, so I'm just going to leave this slide up here. But overall, we utilized the reloaded RM technique on ESPRESSO data of WAS166b and WAS131. The properties are listed there. WAS166, we characterized center to limb convective variations, which allowed us to detect a tentative detection of differential rotation. And for WAS131, differential rotation was the best fit where further precision could result in a center to limb detection. Thank you very much.
Thank you. Any questions? All right, Eric, in the back.
Thanks for that. So if your goal is to just derive an empirical relationship for the center to limb variation, do you need to look at planets, or would grazing eclipsing binaries be better and higher signal to noise?
That's actually a really good question. And so yeah, we could use eclipsing binaries as well. One of the things that I'm actually working on with the NUID team is to get measurements to do the same technique, but with a M-dwarf, brown dwarf system. So yeah, it would be possible, and that's what we're going to try and do.
Okay, great, thanks.
I have time for more questions. I have a question actually. So you compare models of different center to limb functions and then also differential rotations. You have lots of choices, right? So how did you do your model comparison to determine which one you trust?
Yeah, we use the Bayesian information criterion, and then we also use the reduced chi-squared statistic, because for WAS166, I binned the data. And so in order to compare those models, we use the reduced chi-squared as well.
All right, thanks. Any more questions? Or if not, let's thank Lauren again.